Hey there, everybody.
Hello.
Good. How are you doing? So some of you noticed that one of the videos I posted was not working, and I actually found a copy of it that does seem to work. So I'm just in the middle of about to repost that. So let me do that real quick. If you guys have noise in the background, can you mute yourself? Hold on just a sec. So, sorry, give me just a second here. I think this will work now. Okay, I'm back. Yeah, so you might check. I think that video now works. So I think it should be working now. The one I just updated. Let's see, we still have a few people coming in. Good, all right, let's see, before we get started with stuff, any questions from you? It's always good if you have questions.
I just have a quick question about the old last week's homework. It shows that I submitted all of it, but it was on 2 separate pages. You said I need to resubmit because you only got the last portion of it.
Okay,
How do I resubmit that?
Let me go check. I mean, maybe you did something that maybe I missed that. So
Okay.
So usually I'm used to people submitting just one thing, but you might, I understand what you're saying. It's not something I thought about when I was looking at it. So let me just go check that real quick. Let's see, remind me, sorry, I can't see you right now. Remind me who I was just talking to.
Cindy Bjornson.
So let's see, clear filters. What am I doing here? Sorry, tell me your name again.
Allison Bjornson, last name BJ.
Oh, there. Okay. I see. Okay, I did not expect to see that. Okay, I see what I did. So ignore that, and when I get a chance, well, here I'll update the grade, but it's still kind of temporary till I actually look at the stuff.
Okay, thank you.
But that way you don't see the low grade sitting there. All right. I don't know how to make a note. Hopefully I'll remember. Otherwise, you'll just get to keep that grade. Okay.
Yeah, that grade would not be good to keep.
No. I mean, I just changed it to
170.
So if I forget to go back and look at it, then yay.
Okay. Thank you.
Yeah.
And then, Professor, I had one question.
Uh-huh.
I asked in the announcements, or not the announcements, excuse me, when I was asking you a private message, and it was about submitting the homework 2. You have 2 boxes, which is like a homework 2 discussion, and there's another one that's like a homework Dropbox. I submitted my first assignment into the homework 2 discussion portion. I still have some questions like I hoping to get answered in regards to finishing the rest of it up.
Okay.
But did you still want me to submit there, or did you want to submit the homework 2 in the homework 2 Dropbox that originally was on the calendar?
So, I don't have access to what you see when you submit stuff. Can someone be brave and like share your screen and show Aaron how you submitted your work?
I'm sharing my screen if that helps. And so
yeah, so show me where you go to submit homework, and okay. You guys can look too, because I don't see it from your perspective.
So going to the calendar, you have where it says topic 2 homework.
Yes.
Okay. And that's where we're that's the question. But on the discussion forums, you also have, and this was all like part of the announcements, you have homework 2, topic 2 homework discussion, and this is like kind of like you put here, I will post homework here, and you can ask and answer homework questions here. So now there's 2 different locations to post it. I'm not sure if you want one specific or if this is one you want us to post it.
No. So the issue here is that except for homework 1, I
Mhm.
have to tell you what you're supposed to do for homework,
Right.
right? So that's what I'm doing with these topic 2 homework discussion. I'm saying this is the homework you have to do, right? So I gave you the homework assignment, right? So this is where you get your homework from. You need to turn it in the homework Dropbox, right? And then the discussion here is for you guys and for me. So I'll poke into it and look. Actually, I actually forgot about that too. But you can answer each other's questions as well there, right? So you can talk to each other, ask questions, answer questions. That's just a place for you to talk about the homework. But it's also a place for me to give you the homework, right? But when you do your homework and turn it in, that needs to go in the homework Dropbox.
Okay, thank you.
Okay.
Let me stop sharing my screen. Stop share.
Yeah. Okay. Anything else from anyone?
I did have a question about our essay.
Yeah.
I just wanted to make sure like that we turned it in correctly because I know it said to not submit through LOPE, right? Because I haven't got the grade yet, so I wasn't sure if that was like the reason or anything like that.
No, it's just because I haven't had a chance to grade them yet. and also, okay, cool. I'm not going to. Yeah, I'm not going to grade the essay parts with any real stringency. Like I'll look at the math work. But what I tried doing with the essays, so there's a rubric, right? And you're asked to do some things. I'm trying just like running it through AI and saying, give me scores on rubrics. It seems to give pretty positive scores. So I may just do that because I don't know anything about how to format. You know, you guys are the grad students. You have that part. That's your tough part. Yeah, but it's just not graded yet. Yeah, it takes a while. I mean, I have 2 grad classes, and so there's a lot of grading, and your class is really big. So I'm still grading your first homework assignment too, as far as that goes. Good. All right. So our topics today are sort of linear algebra and abstract algebra. And I did meet with one of you to talk about some of the abstract algebra stuff, and I think I want to maybe just repeat part of my conversation. It was Crystal, I think, right? And I might just want to repeat part of that conversation with Crystal because we did a lot of stuff in that meeting. I think we actually talked for like an hour and a half or so.
It was awesome.
So you might have to sit through some of it a second time. And then in the videos, I completely covered Gaussian elimination, except for the fact that the video was messed up. See, sorry, these little pop-ups keep coming up, so I keep seeing things. So now that video is reposted, and I think it's correct. And I go through and solve a very simple system by hand, right? Because it's really simple. It's just a 2x2 system, and I think maybe a 3x3 system by hand. And then I also do it with MATLAB just to show you how to do that kind of in a I'm not really programming it carefully. I'm just sort of literally step by step doing row operations, right? And then in the second video, I do sort of more of that same stuff, but I go a little bit deeper into the way Gaussian elimination is done and some of the verbiage that's got to go along with that. And to make it make any sense, the matrices have to be a little bit bigger, right? 2x2 and 3x3 is just too small to see what's going on. So I think in those examples, I use 4x5 just to get the size up so you can see what's going on. I meant to have a little reading quiz on that stuff ready for you, but just time ran out. So I will try again next week to get that little reading quiz thing to you. When it happens, that'll count for part of your participation grade, but for this week, it'll just be being here again. So any questions on the Gaussian elimination, maybe even on the part that you couldn't watch yet because the video was messed up? I mean, do you want me to go over anything there? Or otherwise, I think I might go on into some of the stuff that I didn't make videos on yet and then go into the algebra part. No one's like anything. I see a few people like nodding. Yeah, let's.
We teach Gaussian elimination in algebra 2. So I don't know. I mean, we don't do it the way with generalized notation, the way you taught me on Friday, that the way it's going to be a grad level. But the basic fundamentals, which is integers and real numbers, we teach that in algebra 2 in high school. So
okay,
I don't think we need that.
okay, I guess the one thing I want to point out, and I tried this in the video, is you do want to do it in a very sort of organized way so that you're always working like from this point down, right? And then you get some stuff and then you from your next pivot down. And so knowing these sort of words like which things are the pivots, that may be something you also do in Algebra 2, I don't know. And then how to deal with free variables and stuff like that, right? So that's important. And the other thing is the fact that you get this decomposition with the columns of the matrix and the sort of parts of the reduced row echelon form, right? That CR decomposition thing, right? So that's probably not something you teach in Algebra 2, I'm guessing. That seems to be a specifically linear algebra sort of topic there, right? And things to know is like the echelon form of the matrix. Is that something you do in Algebra 2? I don't know. Do you talk about those kind of concepts? So like echelon form, as opposed to being diagonal, right? Echelon form is like you have something which is non-zero as a pivot, right? And then you use that to sort of make everything else zero below there, right? And then once you
pivots.
And then once you go beyond that, well, you might have zero here, and you might end up with a zero there, right? So the next pivot would be like there, right?
Professor,
and then
we
once
can't see
Are
your
you
screen.
sharing your screen?
Oh, I'm
Dr.
not sharing
K?
my screen. Nope. I was.
And
Someone
I
else
don't know
was.
about the district I'm in, we don't teach pivots. So I did see the diagonal matrices and all of that when I was doing the reading, but that's not something that we teach at the high school level.
Okay. So I think you can see my screen now, right? It's good now. Okay. Yeah. So what I was saying is that like when you're doing your elimination, right, you sort of look across the top row for the first, leftmost non-zero thing, right? Now you might need to flip some rows around in order to get a leftmost non-zero thing there, right? But then you use that one thing, which is called the pivot, to sort of kill everything below there, make all those zero, right? This row you never touch in some sense, right? And then you go across here and find the next first non-zero thing, right? So in this sort of picture, everything down here should be zeros, right? And then you keep doing that, and you get this kind of, stair step like thing, right? And that's what you use to solve your system, right? And in cases like this, you have these two different kinds of variable, here the variables correspond to x1, x2, x3, etc., right? And these are the pivot variables here, right? And the ones that aren't pivot variables are the free variables, right? And so this is the thing to sort of notice, right? So like, the rank of the matrix, the dimension of the null space, the dimension of the row space and column space, the CR decomposition, all this stuff follows from the Gaussian elimination technique, right? So it's kind of interesting because it's used to solve systems of equations. You're right, you teach that in high school, but it's used to just prove lots of theorems in linear algebra, right? So it's a weird case where you're using a very computational technique in support of the theory that you're learning, like that every vector space has a unique dimension and things like that, right? So you get a lot of stuff out of it. So it's just used for a lot of stuff, right? So it's an important technique to understand kind of carefully.
I think that we teach the process, but not the vocabulary.
I mean, you probably don't teach like what the dimension of row space and column space is, right? Or what the dimension of null space is and stuff like that, right? That's probably going beyond. And we'll get another null space computation when we do the eigenvalue stuff, right? So maybe I'll save that, and maybe we'll just look at one of your homework problems to sort of work that stuff out. So let me get my own notes up here so I can see what it is I want to say. Sorry, everything's in the way here. Let me try to find this. I need a camera that's not attached to the top of my computer. That would be nice. Okay. Let's see. I heard someone say something about the MATLAB, but did someone want to see? Was there something there that you didn't get that I was doing, or maybe we'll when we do the eigenvalue eigenvector thing, we'll sort of look at that from the MATLAB side.
Dr. K, while you looking, what you looking for? For the homework, can we for homework 2, do we have to have like the coding involved in the homework, or can we just write it down and submit it like that, upload it like that? Can it be all written down?
It can be written down, yeah. I mean, like I said, I mean, again, the same rule holds as what I said before. It's good to practice, typing out the math, but you don't want it to get in the way of what you're trying to do, right? So if it becomes too hard to type out, then just write it down.
I submit a question in the homework for everybody to see, but I submitted to you first because I know you familiar with MATLAB. I was trying to do I think it was number 5, I want to say. And from the answer I was getting on my paper and what MATLAB was giving me, I'm just getting 2 different numbers. Even with number 4, I think I did it in MATLAB, and I'm still getting 2 different things each time. I don't know if I'm wrong or MATLAB wrong. I'm like, I don't know. Believe myself or the computer technology.
Well, I can promise you with like 99.9% certainty that MATLAB is not wrong. In the sense of doing something wrong. Let me try to, sorry, I keep having to find stuff here. What did I do with your homework? Where did I put it? I think it's this. Okay. Oh, this topic 1. Sorry. Okay. Sorry. Give me a second. Topic 2 is where I need to be. No, that's not right either. Gosh, I'm just not having any luck finding what I'm trying to find here. Okay, here I go. Okay, let me pull it. Let me just make sure, right? So this is the homework I gave you, right? Let's just verify before I start doing something.
Okay.
Right? Okay, so yeah, we can. I mean, one thing we can do is just sort of work through some of this stuff too. That would probably be a good idea. I want to get through like all the topics, but also sort of working through this. So you said that you tried MATLAB on which one of these problems? Tell me again. Whoever was saying that. 4, 3.
Number 3. I ain't do number 4 was just giving me the blues. I just stopped. I just gave up. Number 3, I think.
Okay. Well, so let me look at the topics I want to cover, and then let's see. Maybe we can just work through that thing. So some topics I would like to. I mean, real quick. Let me just talk about a little bit of stuff. I guess I thought I had links in here to my old, some linear algebra notes.
You do.
Oh yeah.
You got links to everything. I was traveling across the void on all.
Yeah. Okay. Yeah. So yeah. Here's this. There are a lot of good videos and things to go along with this. And what I wanted to do here was so these are the topics we teach in the undergraduate linear algebra. But what I wanted to do here, because writing out matrices is kind of a pain, right? So one thing I did want to do here was talk about the matrix multiplication. And let me just see what I have here. So let me come down to this thing. So one thing about matrix multiplication is there are many ways of interpreting it. And at the beginning of the video, the part that you could watch, right, I gave you 2 different interpretations of what a system of equations could represent, right? So I sort of showed you in R2 how the system of equations could represent 2 lines, right? But it could represent trying to make some sort of linear combination of vectors, right? And then in R, so that was nice to put on one single sort of app that you could play with, right? In R3, you have intersection of planes, right? And then you can do the same thing with sort of looking at linear combinations of vectors. those same kind of ideas come up in matrix multiplication, right? So so here, I guess the way I want to say this is, I'm not sure why I started with my matrix multiplication this way, but I guess I can do that. A is of 1 by n. Let me just make sure I've got the right thing here. B is a n by k. So, okay, so one thing about matrix multiplication, actually, let me pull this over to the side so I can see both, so I can write. Dang it. Where did everything go now? Shoot. Okay. Not sure what's going on. Okay. Hopefully my screen's not doing something weird. All right, so here's some of those notes I have here. So let me just, so one of the things, you know, so a matrix is a, you know, a rectangle of numbers, right? I mean, so that's clear. And generally there's m many rows, right? So these are the rows going across like that, and there's n many columns. Those are the things going down, right? And then if we go to the like the ith row, I mean, some of this you just have to get the notation. I mean, everyone's got to use the same notation, or otherwise things get to be too much of a mess, right? So if I go to the jth column and ith row, so I'm sort of looking at that point right there, right? So let's say this is the matrix A, right? Then that point right there, I might call A. I mean, there's lots of, so I may call it A sub ij. Sometimes we look at the entries of A and call them little a sub ij, and you've probably seen stuff like this too. The MATLAB notation is actually kind of nice because I can just call it aij, right? So it's kind of useful because that matches the MATLAB notation, right? But it is the row first and then the column. Okay. And when you define matrix multiplication, I mean, this is just some numerology to keep in mind. So I have A, which is, say, an m by n matrix, and B, which is a n by k matrix, right? And when we multiply those two things together, first of all, those two inner numbers have to agree, okay? And the result, A times B, right, will be an m by k matrix, okay? So that's, and remember, this is the number of rows in M and the number of columns in B, right? So the result when we do this multiplication will be an m by k matrix with m rows, the same number of rows as A, and k columns, the same number of columns as B, right? So that doesn't tell you how to do anything. It's just sort of a check, right? It's like a numeric check if you try to do something to make sure you're doing kind of the right thing, right? Now, in terms of interpretation, I'm not really sure why I started off these notes this way. I guess I would usually start off this way instead. So suppose I have A. I have my matrix A. Okay, and I view it as having these columns, right, like this. So here I'm going to call this. I guess I'll just call this column A. A1, right? So it'll be the column vector there, right? So this is m by n, right? And so this vector right there is m by 1. So it's got m rows and one column. It's just a column vector, right? In A2, and so it's another vector, right? And we go on down, and we've got n of these because I have n many columns, right? Okay, so I'm viewing each one of these columns as a vector, right? And so so then you multiply it. So now this is m by n. So if I multiply it by a n by 1, right? I can do that, okay? And so these things may be b1 through bn, okay? This is like when I'm looking at a equation like ax equals something, right? So like that, right? It's kind of like that, where the x's would be like those things there, right? So it's giving me a linear combination of columns. So this multiplication here I can interpret as b1 plus the vector a1 plus b2 times the vector a2 plus etc., right? Plus bn times the vector an. So we're adding together these columns. So each one of these is just a column with, in numbers, right? So that's a column within numbers, and I'm adding them. And this is a column within numbers. So the final result is just a column within numbers, right? This will be n by 1. All right. So this kind of, so if I'm doing just a matrix times a vector, right, I would view this as a, so when I say linear combination, I mean, this is sort of some nice words to use. You know, so we have vectors, vectors, and we have scalars, like say these BIs are scalars. So here, maybe these are all over the reals, right? So all the entries are real entries, for example, and maybe in this example, right? So what is a linear combination of vectors? Well, it's just where you have scalar times a vector plus, you know, scalar times a vector plus dot 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 plus scalar times a vector. Right, so that's what we mean by linear combination. So they're the kind of terms you can build in vector spaces, right? You've got scalar multiplication, you have vector addition. The kind of terms you can build are these kinds of things, right? So this is kind of the generic term. So, you know, thinking ahead just a little bit, suppose I had a structure where I had, you know, let's say the reals, you know, plus times 0, 1, right? So now we're looking at, you know, a field or a ring. So we'll talk about this more later, right? But what kind of terms can I build there, right? Well, so here I can build much more complicated terms, right? Because I can like multiply a bunch of things together, you know, x in I, for example, right? And then I can also multiply, then I can also add these together, you know, so I can make these sort of complicated terms that involves multiplication and addition, right? So I can do it like that, or I could even do like a product, you know, where I then take a product of sums, you know, xj, you know, anyway, I can do lots of things like that, right? But in vector spaces, all you have is you have scalar multiplication and you have vectors, right? Which I'm putting a little arrow over to sort of differentiate the two things. And you can't do anything fancy like vector times vector. It's just not defined, right? You can only add vectors, right? Now you can do other stuff with scalars, right? But basically once you apply, you know, distributivity and stuff, you just get back terms that look like this, right? So the most general kind of terms you can get in linear algebra are terms like this. And this is called a linear combination of vectors, right? So like, what would a linear combination of powers of x be, right? So like, you know, like 5 plus 3x minus 2x squared plus, you know, 4x cubed, etc., right? So this would be like a linear combination of, you know, so 1 is sort of there, right? Or x to the 0, you know, up the way, you know, through xn or something like that, right? So polynomials are like linear combinations of powers of x, right? Okay, so I mean, lots of things come in linear combinations, and that's why vector spaces come up so much, right? You also know things from calculus like if I'm taking a derivative, right? I've got cf plus dg, right? So these are functions of x, right? So this is a linear combination of functions of x, right? Scalar times function plus scalar times function, right? And you know that, in fact, the differentiation operation moves through there. I should probably not have used d here, but let's just live with it for a second. G of x, right? So this says that you know, if I take a linear combination of functions and I apply a derivative, I get the same linear combination of the derivatives of the functions, right? So if you've taught calculus, this is sort of a common thing. This is like one of the things you prove and teach, right? Same thing with integrals, right? So there you're kind of using linear algebra in the background, even though you don't know you're doing it, maybe, right? So you're using the fact that integration and differentiation are linear operators on a vector space, which is linear combinations of functions, right? So this sort of stuff is used all the time, kind of hidden in the background, right? Anyway, that's getting a little bit off the track. So my point was here was just that when I went, oops, okay, let me undo that. Undo. Okay, can I just do this? Yep. When I'm doing a multiplication, which is matrix times a column vector, right? That's taking the linear combination of these columns, right, with these as the coefficients, right? So this is like one way of introducing matrix multiplication, thinking of just this case, right? So when I, again, sort of going back to the notes I gave you, when I have something like this, 4, 5, 6, I'm just making up a silly matrix. Some sort of equation like that, right? I could view this as a system of 3 planes, right? But here I'm wanting to think of this as this linear combination of these, vectors here, right? I mean, I guess what I'm trying to say is this is the reason matrix multiplication is defined the way it is, because this is what it's doing. So it's not just you learn some sort of weird definition. It's because this is what it's doing. Right? It's giving you these linear combinations of the columns like that, right? And so if you look at the thing I gave you, right, then I have pictures that sort of indicate what's going on with, with this kind of equation, right, in R3, right? Okay, so that does matrix times 1 column vector, right? So it's really clear, right? So matrix times a column vector is just the linear combination of the columns of the matrix weighted, right, by those coefficients. Okay, is anyone unclear about that? Is that clear? Okay, so that's not sort of a weird definition. It's just that's what it is, right? That's what it's doing, right? Okay, so now when we do matrix times matrix, right? So now I'm doing A times B, right? And so here I have, my A1, up through AK, say, right? And here, over here, I have my, B1, again, columns like this, through let's see, no, I wanted this to be N, right? This was an M by N. I think that's the way I set it up before. And this was like an N by K, right? And so this is through BK over here, right? And so what you can view this as is the matrix of those linear combinations. So it's really A times B1, through A times BK, right? Like that. Okay, so this is just the matrix A times this first vector here. So that's just the linear combination of the columns of A using the coefficients which are coded in B1, right? And then the next column of this product is going to be the next thing over, right? So it'll be the columns of A linear, sort of combined linearly with respect to the coefficients in B2, right? Okay, so this might be a different view of what matrix multiplication is than what you've seen before, right? So I'm viewing this matrix multiplication A times B as kind of coding up linear combinations of the columns of A using the columns of B as the weights, right? So it's kind of giving you a different interpretation of what multiplication is, right? So this is like column-wise multiplication, right? So we can also do this in the other direction using rows. Now, for some reason in my notes here, I start with row-wise up. I know why I do it. So like we can do this instead. I could have a single row vector. So I'll have this still A1 through AN. And over here with B, remember, so this B is going to still be, so now my A, in this case, is 1 by N, right? And my B is still going to be N by K, right? And so now I've got these rows of B. So this is B1, B2 through BK, sorry, Bn as rows, right? Each one of these rows is a 1 by K vector, right? Okay, so when I multiply in this way, I get a linear combination. It's going to be A1, B1. Now this is a row, right? Plus, plus AN, BN. Okay, so this thing right here, so again, those are like the row vectors, right? So this thing right here is a 1 by K vector, right? These are all 1 by K vectors. So we just add them, component-wise. This is like a vector laying on its side, right? Each one having K entries, right? Like that. So you add them together just sort of entry-wise, right? So you can see this sort of left multiplying by a row vector in a matrix gives you the linear combination of rows over here on this side, right? Then when I want to do matrix-matrix multiplication, right? So we can do it like that. So here's my A. Now this will be, again, M by N. So now I've got these rows of A, M many rows of A, right? Each one of these guys is a 1 by N row, right? And then I'm multiplying by these N many rows of B, right? And the result's going to be, basically, so I'm going to build this thing one row at a time. It's going to be, the first row of A times B, right? So it's going to be this row times this whole thing B, and it's going to give me the first row of my product, right? And then I'm going to take the next row and multiply it by B, because these are the rows times B, and I'll get the next row of my product here, right? So like that. Okay, so again, it's a different way of thinking. So you can do matrix multiplication column-wise, kind of thinking of, I don't know, I guess I kind of think of it as with a matrix on the left and kind of linear combinations of the columns on the right. That's kind of what my brain thinks, right? And then here I'm thinking of this as row-wise, right? So now I'm thinking of this as kind of being the matrix on the right and taking linear combination of the rows of this matrix by this matrix A on this side. Okay, so let's see one sort of example. So I think that's the reason in these notes I start off with the row by matrix version, because here's the thing you do. I mean, suppose we're wanting to do Gaussian elimination on some matrix like this. Right, so there's a matrix, right? So the first thing I might want to do is I might want to do row 2 minus 2 row 1 and replace row 2, right? So that might be a thing I want to do. Okay, I can code that easily with a matrix, right? So I can say I can put 1 0 0 here. And what's this say? What's this tell me to do? It says, take one of this first row and none of those rows and add them together, right? So the first row here will be 1 2 3. Because that's what this says. It says take the linear combination of these rows of this thing, right? Take one of this first row, 0 of that row, and 0 of that row, and put them together. Well, that's just the same as 1 of that row, right? Now in this one, right, I want to take minus 2 row 1. So this is going to give me minus 2 of the first row, plus 1 of row 2, and none of the third row, right? And where do I want to stick this thing? Well, it needs to go in the second row, but that's exactly what this does, right? So putting this in the second row here tells me how to do that manipulation over here, right? So now, if we calculate that, what's that going to be? Well, this is going to be 0, and this will be minus 1, and this will be minus 2, right? Yeah. Whoops, right, like that. Does everyone see that? I mean, that's what I get when I do this operation. Right? But I can do that by applying this matrix. Now in the last one, I just want to leave this third row alone, so it's going to be like that, 0 0 1, right? So this will just give me that thing back, like that again. Okay. So applying this matrix, applying this matrix will do this row operation, right? So that's the reason it's not. So that's the reason for thinking of these row times row kind of multiplications, because you code the things you do in Gaussian elimination as row operations, right? You code them with these matrices called elementary matrices. Okay, so so you can. Yep.
Sorry, Dr. K. I'm trying to digest it. So I definitely understand the row operations. I'm trying to see how you got that matrix from those row operations though, in order to perform.
So again, the reason is because like this, right? So let me focus on a particular. So here's my A, right? Here's going to be the ith row of A, right? So that's going to be the ith row of A, all right? And then here's my B, right? So B is going to have these rows. This is an n by k matrix, and this is a what did I say? M by N matrix like this. And there's the ith row of A, right? So what is that going to output over here? Well, it's going to output the ith row of A times this whole matrix B in the ith row, right? In the ith row, that's where it's going to put it because this is in the ith row, right? That's what it's doing. So if I want to replace the ith row, right, by some particular linear combination of these rows, right, then I just have to pick the numbers that go in here as the coefficients of those linear combinations, right? So that's what's going on here, right? My operation is to put in the second row, right? The operation of taking the first row, well, taking the second row and subtracting off two of the first rows, subtracting off two of the first rows, adding one of the second rows, right? None of the third rows, and sticking them into the second place. That's the reason it's here in the second place. Second row down, right? So I mean, you know, again, this is kind of going more into the linear algebra than we need to now. I'm just sort of pointing out that this interpretation of matrix product using row operations is really important for kind of analyzing some of the stuff that happens with Gaussian elimination, because that's what you're doing, right? You're doing row operations, and the row operations can be replaced by these elementary matrices, right? And I'll just get, yeah, go ahead. Who is that?
Yeah, I have a quick question on the row 2. Like, I'm still not quite understanding how do you get the -2 to the 1? So you're saying you're taking 2 of the top numbers. I don't know. I'm still not quite understanding it.
This is row 1. This is row 2, right? I need to have -2 row 1, right? So I put a -2 in the first entry here because that's what it does, right? I mean, again, let's just sort of pull this out again. So look at this one multiplication. No, this is good. Yeah, it takes some thinking. I mean, I would say you want to go think about it some on your own too. So 2, 3, 4, 1, 4, 2, right? So there's the thing I'm trying to multiply together, right? So what does this do? It takes -2 of the first row
by 1
plus 1 of the second row.
So does that mean then that we are taking and multiplying any of the numbers in the top row by -2 and then adding it to the second row?
Yeah, but I don't want you to think of these as being the numbers of. Think of this as being the vector 1, 2, 3, right? The column, the row vector 1, 2, 3, right? So you're taking the first row and multiplying by -2. But you're right. In terms of what you get is -2 times each entry, right? And then you're taking the second row and multiplying it by 1, right? And then you're just adding those linear combinations. You're taking the third row and multiplying that by 0, right? And so what you get when you do that is this row over here, 0, -1, -2. Right? Now the problem is I don't want to just get 0, -1, -2. I want to get the whole matrix that had my original first row, my original third row, and that as the new second row, right? So the whole matrix has to say, do nothing to the first row, right? And it's got to say, do nothing to the third row, right? And what it says to do to the middle row is do -2 times the first row plus 1 times the second row plus 0 times the third row.
Okay, I think I understand. So the row operations are being performed with matrices using linear combinations.
Yeah. Okay. So this is a way of coding row operations by matrix multiplication, right? And so if you when you go through those videos I have, there were these 3 kinds of operations, row operations, right? So there was type 1 is a swap, where you're just swapping 2 rows, right? So what would a swap look like in terms of matrices, right? So if I want to just swap, so 1, 2, 3, 0, 4, I don't know, 6. I'm just making up something, right? 1, 9, 7. I don't know. Actually, let me put a 0 up here and put a 2 here, right? So maybe when I'm doing Gaussian elimination, I would like to swap those 2 rows, right? So maybe that's a thing I would like to do. So how could I do that? Well, I want to take the third row and put it in the top so I can multiply by that, right? I want to take the first row and put it in the bottom so I can multiply by this, right? And I want to leave the middle row alone so I could do that, right? So multiplying by that matrix right there would do the job of swapping these two, rows.
So Dr. K, do you mind if we using like when we like, let's say using Gaussian elimination, if we make the operation as vectors, so or we have to do that way as vectors, or we can do it step by step?
I'm not really sure what you're asking. I mean, what I want you to see, I'm not actually telling you how to do something, right? I'm saying that I want you to see that Gaussian elimination can be done by multiplying by elementary matrices, right? So you can replace what you're doing with Gaussian elimination by multiplying with elementary matrices, right? As a tool, you can do that, right? I'm not saying when you do. So first of all, no one ever does Gaussian elimination on real matrices by hand, right? I mean, you almost always just use a computer to do it, because for real matrices, I mean, when you're really doing something, you've got an image, right? You want to manipulate an image or something like that, right? So you may have 1,000 rows and 1,000 columns. You're not going to do any of this stuff by hand, right? You're going to put it into a computer and say, do this for me, right? But you need to know the theory. You kind of need to know what it's doing, right? So let me give you an example of why this is important. So this would be like a type 1. By the way, notice that in order to get the matrix here, I should go back and look at that previous one too. What I can do to get so remember I wanted to swap the first and third rows, right? So what I can actually do is I can take the identity matrix and do the operation that I want to do. So, row 1 swapped with row 3, right? On the identity matrix, and that gives me my magic matrix over here, right? Same thing up here when I look at this one, right? Let me rewrite this. Let's see. So yeah, so let me rewrite it right here, right? So I had this matrix 1, 2, 3, 2, 3, 4, 1, 4, 2, right? And I wanted to do row 2 minus 2 row 1 replace row 2, right? And so I sort of came up with this by seeing what it had to do as doing linear combinations and stuff. But suppose I just took the identity matrix and did this operation to the identity matrix, right? So I'm going to leave the first row alone. I'm going to leave the last row alone because I'm not saying to do anything. And here I'm going to take row 2 minus 2 row 1. I get minus 2, 1, 0, right? So I get exactly this matrix that I had there, right? So each time you want to figure out what matrix you need to multiply by to get the corresponding row operation, what you can actually do is just start with the identity matrix and do that operation to the identity matrix, right? And then that's the matrix you'll multiply by to get that operation implemented, right? In your original matrix, right? So that's a nice way of sort of seeing what's going on, okay? Yes, I mean, there's elementary matrices for type 1 operations where you're doing swap. There were type 2 operations where you're just multiplying by a constant, right? And then there were type 3 operations where you're doing this sort of take a row, add a multiple of another row, and replace the first row, right? So that kind of thing was a type 3, right? Sort of looking at this a little bit, let me just give you an application of this. You probably know, or maybe you don't know, but you might see it, that I take the determinant of the product of two matrices. This is actually the determinant of A times the determinant of B. Okay. The way to prove this, the only way I know to prove this, is to use elementary matrices in this proof. And use what happens. So you sort of look at what happens when I apply elementary matrices and how those affect the determinant, right? So it turns out if I do a swap, the determinant changes sign by -1, right? If I do multiplying by a constant, which is a type 2 operation, the determinant changes by multiplying by that constant, right? If I do a type 3 operation, which is take a row, add a constant multiple of another row, and replace that first row, the determinant does not change at all. Right, so that's like some of the things you learn about determinants, right? So this tool of looking at elementary matrices and how they relate to Gaussian elimination allow you to sort of prove these kinds of theorems about these kind of calculations you do later, right? Again, you're not taking a full class in linear algebra right now, right? This is just, I'm showing you things that come up, right? Okay. So things to sort of be aware of, right? When you do take the linear algebra class, you'll learn a lot more of this stuff. So I've given you column-wise multiplication, row-wise multiplication, and then of course the other one, which is just kind of this dot product version of multiplication, right? Because that's what most people teach in high school, right? You just take the dot products, rows and columns and stuff like that. But that seems to me, that seems really unmotivated, right? It's not at all clear why that should be doing anything interesting, right? I mean, not until you sort of really get into studying like orthogonality and all that sort of stuff. Whereas the row times row version and the column times column version, those make sense in this kind of interpretation, right? So I think they're good to know, right? It's good to know that there are these other ways of doing it. So that's what I wanted to say about multiplication. There is kind of a block multiplication. Yeah, I guess I'd do something like that here. Like here, I'm saying you can look. No, this is just the row. I mean, you can do things with blocks. Oh yeah, here's the thing with blocks. All right, so I can take this matrix here and I can break it into a block here and a block there, and I can sort of think of this as a block matrix, right? So this is like, it's like taking a matrix A, say this matrix on this side is A, right? And I'm sort of taking it and breaking it into like an A, prime and an A prime prime, right? I'm multiplying it by a matrix B, right? So I can take the matrix B and I can turn it into a B prime and B prime prime, right? So I can take B and split it up into blocks, right? So this is just A split up into blocks. Now the blocks have to make sense. I mean, the sizes have to match up in the right way, right? But then you can sort of just multiply those blocks together too, right? So this is a useful thing to do. And it's a generalization of what we just did with the rows and columns, right? So in the previous examples, I'm sort of saying, take the matrix and break it up into a bunch of rows and do this, right? Or take and break it up into a bunch of columns and do this. But if you want to think of it, you could say, well, I can break it up into any old arbitrary blocks as long as the sizes make sense for multiplication, right? And then sort of blockwise multiply things, right? So maybe it's surprising that there's that much to do with just matrix multiplication, right? There's lots of stuff you can do with it. Let me do say that algebraically, because we want this in a little while, there are some basic things to know. So first of all, when we're doing matrix multiplication, A times B plus C, we do have, and again, all the sizes have to match up, right? But we do get this kind of distributivity, right? So we get that, and we get it on the other side too, like A plus B plus C, times C, right, is equal to AC plus BC. So we get that distributive law. We do not have in general, right? So there's lots of things. So maybe I put this as a warning. These typically fail. It is not generally, it's not generally true that AC equals CA, right? So generally this fails, right? So matrix multiplication is not commutative, right? And because it's not commutative, you also have like this happen. So if AC equals AB, right? It's generally not the case that C equals B. So that generally fails, right? It's also if A, B equals 0, right? It's generally not the case that A equals 0 or B equals 0, right? So lots of algebra that you might expect fail when you go to matrix multiplication, right? So like for this example down here, I can just take something like 0, 0, 0, 1, right? And let me see, maybe 1, 0, 0, 0. So what do I get? So I get 0. Yeah, I think this will work, right? This will just give me 0, 0, 0, 0, right? So I'm getting the 0 matrix, but neither of these are the 0 matrix, right? So when you start working with matrix algebra, you have to be careful with your calculations. You can't assume commutativity. You can't assume what's called cancellation, right? That would be cancellation. You can't assume this thing, whatever it's called, right? I'm not sure what it's called. It's called, I don't know what it's called. I mean, in the algebra class, we'd say these are 0 divisors, but I'm not sure what it's called in general. Does someone teach algebra? Does someone know what this rule is called?
The zero product rule.
Okay, that's a name for it, I guess, right? Anyway, so that rule doesn't hold, right, and for matrices in general, right? So you have to be careful. Now you might look at special collections of matrices where this does hold. For example, if all of the matrices in your collection have inverses, right? I guess we haven't really said what an inverse is yet. Then this kind of thing does hold, right? So you have to be, anyway, lots of little things to look at there. We could go on and on and on. I mean, again, this isn't a full course in linear algebra, right? So there's transposes, there's inverses, there's all sorts of things you could talk about with respect to linear to matrix, just matrix algebra, right? Just the matrix algebra part, much less the linear algebra part. Okay. That's a lot of stuff. Any sort of questions that you have personally on some of this stuff? Again, to some extent, this is just so you're aware of all these things, right? I mean, the only thing I'm checking is what's in the homework, right? So, you weren't asked to do any of this stuff in the homework. So, in the links and the notes I gave you some links to some videos that sort of talk about, I mean, they do this kind of thing too. And they talk about matrix multiplication. If I'm taking, so this, I mean, here's a thing to know. And I think one of the videos that it's the Zach Star, maybe the 3 blue 1 brown, or maybe they both do this, right? So if I take a matrix like this, let's say 1 minus 1, right? So I'm going to take a matrix like that. Because I can do this kind of thing, whoops, x2, right? So I'm taking a pair, right? And what do I get as an output? Is I get another pair, right? And it's going to be 2x1 plus x2, right? And then x1 minus x2, right? Okay. So let's call this A, right? And I can think of this as saying A of x equals y, like that, right? So I'm getting a function, right? I can view A as a function from R2 to R2. All right, and more generally, if I have A as an m by n matrix, right, then I can view A as a function from, and let's see if we can sort of think about this. From what to what? Like, what would the inputs have to be? I'm taking A and I'm multiplying it by some x, and I'm getting out some y, right? So this is an m by n matrix, so how big would x have to be? What has to match up in my
n by whatever matrix?
So like n by 1, because yeah, this wants to be a something by 1 because it's supposed to be another vector, right? So x would have to be n by 1, and this would have to be m by 1, right? Sorry, what am I doing? Yeah. This result will be m by 1, right? Because I have m by n times n by 1 is m by 1, right? M by 1, so when I have an m by n matrix, it basically defines a function from Rn to Rm, right? That's what it's doing there, okay? And it does something very geometric, okay? So again, let's sort of looking at this one example. So in this one example, it's 2 by 2, so it's defining a function from R2 to R2, all right? And if you think about it, what it's actually doing here is it's taking, this sort of standard basis vector here, which often you'll see as I'd like to call it E1, because when you go to higher dimensions, you don't want I, J, K, L, M, N, O, P, right? You want E1, E2, E3, E3N, right? Whatever it is. And then this one you might call J, right? Which I would call E2, right? And then so this would be the 1, 0, right? And this would be 0, 1. 0, right? 1. Okay. And then let's see, we get this little like square here, right? The unit square right there, right? And so what does the matrix do? Well, it takes this vector here and moves it to 2, 1. So that may be here, right? So it's gonna, let me change colors here. So it's gonna like take it and turn it into that vector. In fact, I'll just do it like that, right? And then this vector here, 0, 1, is going to get mapped to 1 minus 1, right? So that's going to be 1 minus 1. So it's going to get mapped to down here. All right. So this vector here, so E2 is going to get sent to this column, 1 minus 1, and E1, which is I, right, is going to get sent to this one, which is 2, 1.
2 minus 1.
Right. So what's happening is you're sort of mapping this square, right, onto, well, like a bad picture here, right, but onto this corresponding parallelogram with those sides. Right. So that's what it does. And so you can kind of think, you can use this to think about how functions are what happens to shapes, right, as you do this kind of thing, right? So like, what would a circle get mapped to? This is definitely bigger than that, right? So it's going to get blown up into something that stays circular, but it's also going to get stretched more this way than that way, right? So it's going to become this kind of, if I took a circle here, it's going to be kind of stretched into this elliptical thing here, right, into an ellipse, right? And this is like super, super important. So do any of you teach like Calc 3? Are any of you interested in teaching Calc 3? Okay. So, I mean, again, right, what's a derivative? A derivative is a linear map, a linear approximation to a function, right? So if I have a function f going from R2 to R2, right? So how would I draw such a thing? So maybe I have a copy of R2 over here, and I have a copy of R2 over here, right? And maybe I have some shape over here, or whatever it is, and it gets mapped to some shape over here, right? And so there's a map f that does that. So what's the derivative? Well, the derivative f prime is the best linear approximation at each point of this f, right? So what's happening here is like little squares over here are getting mapped to little trapezoids over here, and the size of this trapezoid is kind of given by the matrix that's doing that, right? So it turns out to be the determinant of the derivative at a point, right? Something like that, right? So lots of interesting linear algebra and matrix transformations and stuff going on when you're doing multivariable calculus, right? Anyway, so lots of good, interesting stuff here to think about and learn. And I mean, to some extent, I guess I'm trying to say these are all things you will learn in the future, right? Let me see if I can keep somehow 2 things open at once here. Okay. Okay, quickly. So that's really kind of the multiplication. So I do. So I'll just pull this down here, right? So if you don't like the way I'm saying it, there are these 2 really nice videos here that go through this too, right? So I suggest watching those because they're nice, easy to watch, good on the animation. If you don't watch 3 Blue 1 Brown, you ought to, right? For teaching math. I mean, it's a great website for stuff. Let's see. The only thing left here. Well, there's 2 things. There's abstract vector spaces. Let's hold off on that. And then we have the eigenvalues, eigenvector stuff, right? So let's look at the eigenvalue, eigenvector stuff because that sort of fits in better with what we're doing. Let's see. Someone tell me the problem you actually have. Let's just sort of work through this by hand. So you were finding the eigenvalues and eigenvectors of something. What was it?
It's the matrix D, which equals going from top to bottom, and the first column is 4, 2, and then the second column is 1, 3.
1, 3, like this. Okay. So this is a matrix D. So thinking in terms of this transformation thing I was just talking about, right? So this is our matrix D. What we're looking for when we're doing eigenvalues and eigenvectors, we're looking for x's that have the property that when I multiply them by D, it turns out that all it does is stretches in that direction. Right? So it turns into just scalar multiplication in that direction, right? So remember in general, I had this like little square and it got turned into some sort of, thing like this, right? So if you just look at how points move instead, right, then what happens here is I would have like a vector x bar, and in this direction, all that happens is my x bar gets stretched out to lambda x bar. Now it could be could be negative, so it would get turned around as well, and it could be less than 1, so it could get shrunk, right? So when I say stretched, it could be made longer, it could be made shorter, right? Either one of those two directions, right? But basically, you end up with this, in this case, like a line through here. So there's like the actual vector x is like right there, right? But you get all the linear combinations of x, and so that would be the eigenspace u lambda. So sort of the space of all the linear multiples of that thing, right? So once I have an eigenvector, so this would be an eigenvector eigenvalue pair. So they come in pairs like this, okay? And once I have an eigenvector, well, t times x is also an eigenvector, right? Because if I do d of t times x, that's just going to be t of dx, right? And that's just going to be t times lambda x, right? But that's just lambda tx, right? So if x was an eigenvector, then tx is also an eigenvector, right? So anything in that line, right? And this is a subspace, right? So maybe that's where skipping the vector space stuff is not a good idea, because I'm talking about subspaces here. In this case, I'm in D2. So if I had two of these eigenvectors, say I have one eigenvector going that way and one eigenvector going this way. Now here's something else that we're not getting into deeply here, but in 2 dimensions, once I have 2 non-parallel vectors, I can build any other vector from those 2 vectors. Right. So say I had this is my, this is my lambda 2 x2. So I have my second eigenvector, and let's say this is lambda 1 x1, right? And I take any other point out here, some z, right? Then z will be some linear combination of those 2 vectors, right? Because, well, and I sort of do this in the pictures. If I want to reach z, all I have to do is sort of come out along here far enough so that if I go in this direction, right, which is kind of like this, right, I can get to z that way. So it's like stretching this z a little bit to get to there, right? And then just figuring out what scalar multiple I need of here, right? So I get this little parallelogram, right? So that's basically, so I mean, this is like proof by picture that any z in R2, I can reach from those 2 vectors, right, by taking scalar multiples, right?
This is a kind of normal vector when it's perpendicular out of the plane.
So I'm not saying these are perpendicular. These may not in any way be maybe that's a bad picture, right? So let me make one that looks a lot less perpendicular, right? So let's say here, so one of them might be like this. So this might be my e lambda 1, right? So maybe my vector there is that x1 right there, and my other one might be like this. Right, this may be my e lambda 2, and so my x2 may be, in fact, the x2 could be going this direction for all I know, right? It could be x2 like that, right? Now, if I take any point anywhere in this plane, here's a random point over here, I can reach this point by some scalar multiples of, added scalar multiples of those 2 vectors, right? So I just need to get to some place where if I go, I can go in a negative direction, right? So I can think of myself in going that way too, but I just need to take some way of making a parallelogram that reaches this, that has sides that are in these directions. Right. And so you can always do that. I mean, I'll leave it to you. This is an easy thing, like if you play with Desmos or something where you can animate stuff a little bit, right? You can just put in, like AB for this vector and CD for that vector, EF for this vector over here, and just see how you move things around so that you eventually get things to move, right? So you can do that. It's kind of like the picture I gave you earlier in these notes, right? So it's essentially the same idea is what I have going on there. But the point is I can write them as linear combinations like that. And then when I want to see what D does to anything here, so DZ, well, because of our matrix algebra, that's going to be alpha dx1 plus beta dx2. All right, so as soon as I, so I can, use the algebra to do that, but this will now be just alpha lambda 1 x1 plus beta lambda 2 x2. All right, so once I sort of break things up into my eigenspaces, right, I can easily compute D of something because I just apply D to each one of these things and just multiply by lambda, right? And the beautiful thing about this is if I want to apply D 1,000 times, right, to my Z, I'm interested in where Z moves over 1,000 periods or something like that, right? So this is really used when you think of things moving or changing in space or something like that, right? Then this would just be alpha lambda 1 to the 1,000, x1 plus beta lambda 2 to the 1,000 times x2. Because along these directions, right, you just keep multiplying by scalar multiples of lambda 1 and lambda 2 as you repeat the thing. Now, computing this is a pain. It can, even for a 2 by 2, computing d to the 1,000 can be a real pain, right? But computing this is not. You're just taking a power of a fixed number, right? So that's easy. Okay, so that's like part of the reason that eigenvalues are so important. I mean, this is really part of the reason eigenvalues are so important, because you can really, really simplify repeated matrix multiplications a lot if you take the matrix and first find an eigenvector basis for the matrix. Okay. So now in your case, you're asked to compute this thing. You're not really asked to talk about what it means and all that stuff. So how do we compute this? So again, what I'm looking for is I'm looking for an x and a lambda, right? The thing that's weird here is you're trying to find two things at once, right? Such that dx equals lambda x, right? So that's what you're trying to do. You can rewrite this as a matrix equation, right? So you can say dx equals lambda I x. So I'll just do this in a few steps, and I can subtract and get dx minus lambda I x equals 0. That's the vector 0, right? And so I can do this as d minus lambda I x equals 0, right? And now this is something that that I say in the video. So here, so let me just sort of say on the side, if I have a matrix A and I'm looking at AX equals 0, so I'm looking at this, right? So this kind of system of equations would be called homogeneous because I have a 0 on that side specifically, right? And if I look at the set of all x, such that AX equals 0, this is a subspace. It is actually a vector space itself, and it's a subspace of the original space. The original space is like, maybe this is an Rn, right? And this is called the null space of A. Now, some of you have already written this in your work, and someone said something about this earlier in the class, right? So, right, what you're doing here is you're taking this d minus lambda I, and in order to find the eigenvectors, you're finding the null space of d minus lambda I. That's what you're doing, right? How do you find null spaces? Well, Gaussian elimination does it, right? That's exactly one of the things that Gaussian elimination does. Did someone have a question? That was a hand up or something. Oh, I heard a sound. Crystal, did you have a question? Maybe I'm just now seeing it. Okay. Maybe that was some other sound.
It was a long time ago and I didn't write the question down.
Oh, okay. Sorry. Again, it's hard for me to sort of look over there and see that at the same time. You notice I'm always looking down because the thing I'm writing on is down and my camera is way up there somewhere. Maybe one of these days I'll find a way of making that better. So let's do this thing for this particular matrix, right? So there's our matrix, right? So let me just rewrite what I actually want to do here, okay? So we want to do two things. We want to find lambda such that, and let me just use this notation, such that the null space of d minus lambda I is not just the 0 vector. So there's more than just, so it's always the case for any matrix A times 0 is 0, right? So 0 is always in the null space, right? Now, when we're interested in eigenvectors, we want non-zero eigenvectors, right? They need to be non-zero. So we're looking for a place where the null space is not 0. Okay, so that's like one thing we need to do. Once we've done that, then we want to actually find, and now I need to say what I mean by find, find the null space of A minus lambda I, or D minus lambda I. Well, I mean find a basis for the null space so that we can describe the entries in there nicely, right? That's what I mean. Okay, so we'll do these two steps. Now in step 1, how do you actually do that? So it turns out that the null space of A is not the 0 vector. In fact, I'll do several things here. By the way, this is always for square matrices. When we're doing eigenvalues, eigenvectors, these are always n by n, right? So these are always square matrices. So this is 2 by 2 in this case. So this is the case if and only if. So various things. So there's lots of things I can see here. A is not invertible. So that's one thing. If and only if, and so another thing is that the determinant of A is 0, right? So that's another thing. And there's other things you could write here, okay? So it's this one that we focus on because the determinant of A is basically a polynomial in the entries of A, right? So this is kind of like asking, is a certain polynomial 0? And as long as the polynomials are pretty simple, so remember that, Crystal, because maybe it's important. As long as the polynomials are pretty simple, maybe you can find the roots, right? Or maybe you can just write out the polynomials and use a root finding thing on a calculator or something, you know, to try to figure out what the roots are. So sort of putting all that together, right, in order to find this lambda, in order to do step 1 here, right, I want to find lambda such that the determinant of d minus lambda I is not 0. Is 0, because I want to find out is 0, right? Is 0, right? So our d was 4213. So d minus lambda I is 4 minus lambda, I forget, 1, 2, 3 minus lambda. That's our d, right? How do we find determinants of 2 by 2 matrices where you cross multiply and then you subtract the one going that way, right? So this is 2 by 2s are really easy to do, and you get a quadratic, so you know you can always find a root, right? So in this case, the determinant is 4 minus lambda, 3 minus lambda, and then minus 2. I mean, if you like, minus 2 times 1, just to make that clear, right? So that's the determinant of d minus. All right, the determinant is that thing there, right? And then, of course, you just sort of multiply this out. So this is 12 minus 7 lambda plus lambda squared minus 2, right? So this is lambda squared minus 7 lambda plus 10, right? And again, here, this is quadratic, so you know you can do this. And this is easy to do, right? It's lambda minus 5 and lambda minus 2, right? And that's it, right? This can only have 2 roots, and there they both are, right? So those are the only things that can possibly be the eigenvalues, right? So doing it this way, what you do is you find the eigenvalues first, right? So now we've found our eigenvalues. Okay, any questions about that part, by the way? I'm not seeing any, okay. So the next thing you want to do is find the eigenvectors. You really find the whole space. Go ahead. Was someone going to ask something?
Crystal have her hand up. I'm not sure if she'd ever take it down.
I think she has a question about inverses. So let me finish this, and then we can go back and pick up the inverse question. So to finish this, right, I need to do this step 2, right? So step 2 was find the null space of d minus lambda I. Now you need to do this for both of these, for 5 and 2, right? So I'll do it for lambda equals 2, and I'll leave it for you to do lambda equals 5, you know, on your own. I mean, you need to do all this on your own, so you should go back and redo it all. But I want to find the null space of, now what is d minus 2i? So let's just write it, d minus 2i, right? So this is the null space of 4 minus 2, which is 2, 1, and then 2, 2 and 3 minus 2, which is 1, right? Like that. All right. So what we're looking for here is the set of all x such that 2, 1, 2, 1 times x1, x2 is equal to 0, 0, right? That's what it means to be the null space, right? We're looking for that. Now in 2 by 2 cases like this, you can usually just look, right, and see. I mean, so these 2 columns are the same. So really all I need here is I need that, you know, 2x1. I mean, if you want to do it algebraically, right, 2x1 plus x2 has to be equal to 0. right? So that's what you need to solve. And of course, you know, there are infinitely many solutions. I told you that before, right? This is all space. It's all space of solutions. Now I want a basis, so let's actually do this another way. Can you think of a single vector here that works? And so you can say, I mean, definitely this vector works, right? 1 minus 2. Right? So if I do, you know, 2, 1, 2, 1 times 1 minus 2, I get 0, 0, right? Okay, so so the space, now here's where we're sort of avoiding the theory. There's two distinct eigenvectors. So we know from the theory, which we aren't discussing here because it's just too much, right? It means that there will be two one-dimensional eigenspaces because we're only in R2, right? So each eigenspace has to have dimension at least 1, right? We can have at most 2 of these because our space is only R2. And so there can only be 2, right? So once I have 1 of these, I know I'm done because the other eigenvalue has its own eigenvector, right? The other eigenvalue, 5, has its own eigenvector, right? So this works. So the whole space, whatever the space is, will just be the set of all t times 1 minus 2, where t is in R. Right. So I mean, what does this multiplication do, right? So we're sort of, if we think about this as doing a transformation of the plane, well, I mean, I can just do it here. Well, I mean, you know, you take a point and it sends it somewhere, right? Let's do it on the same shape. So 1 minus 2 is like 1 minus 2. So maybe here, right? All right, and what does it do to points along this line? Say I have the line going through there, right? What it does to points along that line is it just stretches them by a factor of 2, right? That's what the eigenvalue 2. So it just stretches points on that line by a factor of 2. That's what it does, right? That's what the transformation does. And then you do the same thing. You find the null space. In fact, let me just let you do that, right? Find the null space of d minus 5i, right? That's the other one, right? The two eigenvalues were 5 and 2, right? So what is d minus 5i? So this is a null space of, what was it, 4? It was 4 minus 5, which is minus 1, right? And what's the other number there? 1, right? And 2. All right, and 3 minus 5 is minus 2, right? So can you think of a vector so that when you multiply by that matrix, you get 0?
Professor, is that the notation you want the homework in?
I forget what the homework asks. I think it just asks you for an eigenvector, doesn't it?
It asks for both the eigenvector and the eigenvalues, but I'm just wondering, the way you wrote it out with no space, is that the way, would you want to see that when we turn in our homework?
Well, no, I mean, because what you're actually calculating here is the whole eigenspace, right? So finding an eigenvector is just this one step I'm saying now. What could you multiply this matrix by to give me 0, 0, right? So you've got minus 1, minus 1, 1, 2 minus 2 times something, and someone just said it, 1, 1, right? Will give me 0, 0, right? So in your homework, you need to write down that vector and 5, right? But here, the whole eigenspace is that, right? So that's the eigenspace. And so coming back up here, right, that's like this vector, right? That may be 1, 1 there, right? And then you get the whole space is going through like that, right? So everything along this line is multiplied by 5, right? So when we stretch it, when we apply the map once, right, we get all the way from here out to 5 times that thing, right, out there. So like 1, 2, 3, 4, 5. I mean, that's not a good picture, right? But something like that. So you can kind of see, right, if you just dropped a point in here, what's going to happen? What's going to kind of move 5 times faster that way, and it's going to twice sort of in that direction, right? And then maybe you could try to figure out like how it moves in this thing, right, based on that. right? It's going to kind of move down a little bit, but it's going to move further. So I don't know, maybe the motion's sort of like that. I don't know. Right. So this is again where you might use computer to sort of see how points move, right? And you'll do more of this next week when you do differential equations, because the same kind of stuff comes up in solving differential equations. I mean, you can kind of see that going on here. I'm looking at how things are moving when I have directions I can go, right? That's sounding very differential equation-y, right? Okay. So anyway, you need to go back and redo that again on your own, right? But yeah, I mean, all the questions asking you for is the eigenvector eigenvalue pairs, right? Okay. And again, I gave you some videos. So in the notes, I say eigen things, and I have a video from Zach Starr, and he's got a lot of applications of this, right? So it's a good video to watch if you want to just get an intuition of what's going on here. Okay. Any questions about that?
Okay. I just have like a nitpicky question. Instead of x1, x2, is it okay if we call them xy?
Yeah, that's fine. I mean, it's just get used to using subscripts, right? Because when you get into actually get into 512, right? You're always having to do things like, xi, vi, you're having, I equals 1 to n. I mean, you're having to do proofs with stuff like that, right? So you have to get used to using subscripts, right? And so like when I say ei, if I'm in R n, right? So this is like the vector that's got a zeros, every 1 here, and then a bunch of zeros, right? And its length is n, right? It's got n many entries, and this is occurring in the ith place, right? So stuff like that. So I mean, one of the things about linear algebra, it's full of indexing, right? You just have to get used to dealing with indexes all over the place. So I mean, that's the reason it's sort of nice to break you of using ij and then to start using e1, e2 instead, just because that's what you have to do, right? And instead of looking at xy and xyz, it's good to break the habit and start going to x1 through x15, whatever it happens to be, right? So that just to get used to that, right? Because that's the way things will be, right? You have to get used to that. Okay, let me jump into. So what I didn't do here is I didn't talk about vector spaces and vector space axioms. So let me just do that really quick, and then let me jump into the abstract algebra part so that you see it. And if you have any questions, and by the way, Crystal had a question about multiplication. What was that? Or inverses? You're muted right now, so.
Yes, sir. I was reading through one of your assignments, and it was talking about inverse. It had lambda times the matrix times the inverse lambda, and I think that's what you did earlier when you said the identity property times the inverse of the identity property, but I'm just not sure how that applies to what. I mean, it didn't have anything to do with the homework. It was just me doing some reading, and I just kind of got lost with inverse matrices.
I mean, so inverse matrices, and maybe talking about the abstract algebra will help there, because matrix multiplication, matrices with multiplication form a kind of algebraic structure called a ring, right? And so you do look at like which things have inverses, which things don't have inverses. So a matrix. So first of all, it's got to be an n by n matrix in order to have an inverse. Okay, and what it means to have an inverse is it means that there's some matrix B such that AB equals I and BA equals I, and that's it, right? So you need, but yeah, I mean, you need both of the, I guess I already said that, right? No, what did I do? I wrote that twice. You need AB equals I and BA equals I, right? And in that case, so here's like a little tiny proof, right? So could there be more than one such B, right? Could I have two B's that have this property? Could I have AB prime equals I and B prime A equals I? And here's a place where you could do proof by contradiction, or you could do direct proof, right? We actually have lots of options we could use here. I want to show that B and B prime are the same. So one way would be to say, let's do proof by contradiction. Let's assume B and B prime are different and get a contradiction, right? So that's a thing you could do, right? On the other hand, you could just do a direct proof. So let's say B, right, is equal to BI. Now, what is I? Sorry, maybe I should be careful here. So I is the thing that just has ones down the middle, like that, or ones down the diagonal, right? And so I has the property that AI equals A equals IA always. Okay. So B equals BI, right? Now I'm assuming that I is equal to AB prime. So this is B AB prime. Okay. One of the things we didn't do, so matrix multiplication is associative, right? So we can associate here and do BA B prime, like that, right? But BA, also by assumption, is I, right? So this is IB prime, and this is just B prime, right? So assuming these two things, right, I get that B equals B prime, right? So there's only one, right? If there's an inverse, there's only one, right? And since there's only one, we can give a name to it, and we can call B equal to A inverse, right? And so what A inverse means is it means that there is a B such that A, you know, the property it has is A inverse A equals I equals, sorry, A inverse equals I equals A inverse A, right? Okay. It's like having an inverse map, right? In fact, it's exactly like that because we can think of A as being a map, a map from Rn to Rn, right? I sort of mentioned that earlier. And so a matrix map going from Rn to Rn has an inverse if and only if that map is invertible. So 1-to-1 and onto. Okay.
You lost me at B equals A inverse. I don't know where the A inverse came from. I was still writing.
So this is what we did up here. I showed that if there was something that satisfies both of these things, the requirements for being an inverse, then that thing has to be unique. That's what we showed up here, right? If I have two of these things that both satisfy this, then they have to actually be the same thing, right? So it's unique. So once I have that it's unique, I can define it, you know, I can give it a name, right? So the point is when I have an inverse, when A has an inverse, I can say there's a unique inverse. So I may as well just call it A inverse, right? I mean, like if there were two inverses for 2, I mean, suppose 1/2 and 1/4 when you multiplied it by 2 just gave you 1, right? Then you couldn't call one of them A inverse, right? You'd have to say they're both sort of A inverse, but that's not the way things work, right? So when there's an inverse, there's only one inverse, so you might as well call it A inverse, right? What you don't want to do is you don't want to do something like 1/A. That's bad notation because remember you don't have commutativity, right? So you don't want to accidentally use commutativity here, right? Good. Okay. So real quick, let me save vector spaces because they're actually the hardest set of axioms compared to all the others in some sense. Let me just go through these sort of abstract algebra concepts really quick. Let me see. Let me pull this. I guess I need this down here. Okay, so this I haven't given you a video on yet. I'll add it, right? But oh, sorry, what did I do? This is yeah, okay. Forget the number theory for just a second. That's actually what I wanted to show you. You know, Crystal, I should have just recorded our meeting and I could have just put that out there, right? As because we did a lot of interesting stuff with this, but we're gonna run out of time, so let me just jump to this stuff down here. So now this is really a level up in sort of an abstraction, right? So I haven't said yet what an abstract vector space is. So I mean, that too would be a level up in abstraction. So far we've talked about Rn, Rm, you know, things that you're familiar with, right? But you can generalize algebra, right? And so groups, what are they? They're just a set. And this is part of the reason you do the set theory stuff. So it's a set. And a binary operation, I'm just going to call it dot. Okay, in the notes I call it star. If you need to indicate that it's a specific binary operation for G, you might put a G subscript there to make that clear, right? But I'm just going to put a dot. And it's got a kind of identity for whatever that dot is, okay? And so now this is where the logic stuff comes in. It satisfies some axioms, right? What has to be true about this set, this binary operation? So dot is a map going from G cross G to G. It's a binary operation, right? E is an element of G. That's all you know about it so far, right? And I'm going to give you some axioms it has to satisfy. So first of all, it needs to be associative. Okay, so I need to know that A dot B dot C equals A dot B dot C. And when we're using this kind of multiplicative notation, it's really common just to drop the dot. All right, so like that. All right, so the usual associative law. E is a dot identity. So what that means is it means A dot E equals E dot A equals A, right? So the whatever this binary operation does, when you put one side or the other to be E, you just get A back, right? So that's an axiom it has to satisfy. And 3, we have dot inverses. Okay, so this says that for all A in G, there exists a B in G, such that A, B equals E equals B, A. Okay. Those 3 axioms tell you what a group is, right? So anything satisfying those 3 axioms are a group, whatever they happen to be. So can you think of some groups?
Integers?
Yeah, the integer is under what operation? We got to give the set, the operation, and the zero.
Multiplication.
Okay, so that's a good one because it's a little bit wrong. So, oh, sorry, what's the identity under multiplication?
1.
So the identity would be 1. Actually, it's a great example because it is actually quite wrong in some sense.
Okay.
Which one of these axioms has so we're saying multiplication, and this is our E, right? But does 3 hold here? Like
No, because when you divide by an integer, sometimes you don't get an integer. Is that why?
Yeah, in fact, most of the time, right? Like 2 times what would give me 1? Well, I need a half, but this is exactly why we invented rationals, right? It was so that we could divide. Okay, so yeah, so it is a nice example because it's sort of a non-example. It's a great kind of non-example. Now sticking with this, so now there's 2 sort of obvious ways to go. Is there a way to fix this example and maybe in 2 different ways? So one I just kind of said, one way would be to, well, let's try to add in inverses, right? So if we try to add in inverses, what structure would I have?
Real numbers?
Well, just inverses for Z, I would just be adding in things like 1 over 2, right?
Also rational numbers.
Rational numbers, right? So Q. Now there's actually still a problem here, and we'll think about that, right? But so now we're saying, well, maybe this is a good example of a group. Now, is there actually still one problem here? Like, can you think of something that just never has a multiplicative inverse?
You can't divide by 0. Is that it?
Can't divide by 0, right? So we actually take Q star, which is Q take away 0, right? Okay. So this is or you could even take just positive rationals, right? Because if I take 2 positive rationals and multiply them together, I still get a positive rational, right? So you could either just throw away 0, or you could just take the positive rationals, right? But now this is a group finally, right? So that's one way of fixing it, is to go to that group. What's another way of fixing it? Instead of using times, what could I do?
Addition.
You could do plus with 0, right? That would be a group. Right. So yeah, and so once you see these, you got lots of examples, right? You have R star with times and 1, right? And you have, that would be a group, right? And you have C, right, with times and 1, right? And you have corresponding, R with plus and 0. right? C with plus and 0. You know, all sorts, right? All sorts of, I mean, these things generalize numbers. What else do groups generalize? So for example, if I had, so here's an, I'll just give you this one because it's kind of interesting. Like I have a shape like this, right? So this is a hexagon, right? Right. So pretend that was a perfect hexagon, not what I actually drew, right? And then how can you change this into a shape that looks exactly the same, but where you've moved things around? So say I label these points A, B, C, D, E, F, right? So I can do things like rotate 1/6 of a circle, right? And if I did that, I get something that sort of clicks this thing around, right? So the A will move to B, B will move to C. So it kind of does this clock-like thing, right? But I get a shape that looks exactly the same, right? So it's like, it's got a little cutout area it sits in, right? It's got to sit in exactly the same. So those kind of transformations form a cyclic group of rotations, right? So there's a cyclic group of rotations. Is there some other transformation I could do here that would keep the same shape?
You can flip it over.
You can flip, right? So flip around there, right? So you could flip around there, around there, around there. So this gives me a group called, yep. Sorry, what was that?
That would make it symmetrical, right?
Yeah. So I mean, so these are all symmetries of this shape. And so this gives me a group called D6, which are the set of symmetries of a 6-sided regular polygon, right? And you have this for everything. You have D3, which would be the set of symmetries for an isosceles triangle. The sides have to be the same length, right? D101 for whatever a polygon is, right? So you get these groups that you'll study a lot, like in 513, right? So symmetries of objects are groups, right? Any kind of symmetry I do, I can undo it by just undoing the symmetry, doing it backwards, right? All of the permutations of n objects, right? So if I just take 1 through n and permute them in all various ways, right? And I combine those permutations by, permuting in one way and then permuting in the next way, right? The set of all those permutations is a group, right? So the set of all functions on the reals that preserve distances. I mean, there's so many groups, right? So groups are just all over the place in math, right? So it's like a very general sort of structure that we study, right? So they kind of generalize rings, but they also generalize symmetries. They generalize one-to-one functions, all sorts of things, right? So groups are a really, really general thing. One of you in your write-up said something about just looking at the associativity property as a single axiom, right? And so this has more than that, right? Because it has associative, it's got the identity, and it's got inverses, right? And it's got very different looking groups. So this is like answering one of your questions, right? So it's got these groups up here that look like numbers. It's got these groups down here that look like all the symmetries, right? But very different models for the same kind of algebraic structures. If you just keep the identity and throw away inverses, then you get something called semigroups, right? So that's another set of structures that are studied. If you just throw away everything except associativity, I don't know that that's called anything, but it might be, right? A pseudo semi group. I don't know what it might be, something, right? I mean, you're losing a lot of structure there, right? You're getting really close to just being a set, right? So a set is kind of the thing with the very least structure. It's just stuff, objects, right? No structure on it. Okay. So the more axioms you put on it, the more structure you have. So that's groups. Rings, right? I'm just gonna have to do this fast because we're gonna run out of time. A ring has a set. Now it's got a thing that I call plus, and it's got a thing I call times, and it's got a thing I'll call 0. Okay. And these have the property that this part of the structure is a group. Okay. And the only other thing I know, well, I know 2 other things. I know one thing, which is that the product part is associative. So associativity is really, really important in these things. So we got the associative law for product, and we've got distributivity. Now you need two of these. Whoops, C plus D equals AC plus AD, and C plus D times A equals CA plus DA. Whoops, I lied a little bit. Not only is this a group, but it's commutative as well. So a commutative group. So you get one more axiom. You have commutativity as well. We don't assume commutativity of multiplication. So this you really need both of these, right? If it was commutative, you could get away with just one of those. Okay. So that's what a ring is. So what are some good models of rings? Matrices under multiplication with entry-wise addition, right? So n by n matrices under multiplication, not commutative, but they satisfy these rules, right? These are like the matrix multiplication rules I wrote down before, right? There in a ring doesn't even have to have a 1 in it. If we look at the ring of matrices, there is a 1. The identity matrix acts as a 1. It acts as it's a multiplicative identity, right? But not every matrix has an inverse, and some matrices are, some like two non-zero matrices can multiply together to give you 0, right? So there's all sorts of that kind of stuff can happen, right? So if you want to sort of really abstractly study matrices, you might study rings instead.
Is that why we would group matrices to create a square matrix so that we could find the inverses?
So I'm not sure what your question is. So the only kind of matrices that can have inverses are square ones.
Right, and you showed n by n's being multiplied with some larger groups of matrices, and then you showed them how they were broken into groups or chunks. I don't remember the word, but the bottom line is that you created a bunch of groups of square matrices. So is that the purpose for doing that?
No, that's really different. I mean, that's a matter of just so that's really less of an algebraic thing and more of a I'm not sure how to explain it. More of a combinatorial thing, right? So I'm sort of looking at different ways to break up. I mean, you're just thinking of those as like a big array of numbers, right? So you're doing something with arrays and breaking stuff up that way, but you're not really doing anything algebraic there, right? So I mean, that's one of the things. Matrices have two very linear algebra is really interesting because it has various sort of different kinds of applications. Some of them are very algebraic, and some of them are really computational, right? And you some of the times you want to do everything in linear algebra just using the algebra, and some of the times you want to do things in linear algebra really using the structure of matrices, the fact that you have this grid of numbers, right? And the two things feel very unrelated in some sense. I mean, so it's sort of that's part of what makes it interesting. Yeah, but that was sort of a different thing. What are some examples of rings? So some should be obvious, right? So is Z a ring? So is the additive part a additive group, right? And we just looked at that a minute ago, and the answer was yes, right? It's an additive group, and it's commutative, right? So that's good. We know that it commutes, and the multiplication part definitely satisfies this stuff up here, right? So Z. This is sort of a very typical example of a ring, right? Q plus times 0, right, is a ring, and these rings also have ones, right? So we could even throw a 1 in there. So when we have ones, we say they're rings with unity, right? And they're commutative rings because multiplication is commutative in those particular rings, right? Again, non-commutative rings are things like all matrices, all n by n matrices. That's a non-commutative ring where we're using matrix multiplication. The addition would just be matrix addition. Matrix addition is a group, right? I mean, I can subtract two matrices. It's commutative, all that stuff. Yeah,
sorry.
Go ahead.
So Dr. K, so I kind of had a question about this one because the integers in modulo n would be a ring, but I had trouble kind of proving that with the axioms listed.
Yeah, so that is the thing. That's exactly the thing Crystal and I spent an hour and a half talking about. So I sort of wish I had, and maybe it's fortunate because I can reduce some of what we said. Let me say what a field is first, and let me say what a vector space really quick, and then let me sort of hint at what has to go on in that, and then maybe I'll add that to the videos I have because that was an interesting discussion because that involves the number theory and all sorts of other things too. So rings have a group structure and they have some other structure. Fields, so this is like a field F plus times 0, 1, right? So what happens here, in particular, a field is a ring, but we have is that F plus 0 is a commutative group. And F star, remember that's where we just throw away the 0, times and 1 is a commutative group. And distributive laws. Okay, and the sort of classical examples of fields are the rationals. That's the smallest field that contains the integers, right? The reals is kind of the smallest field, which is complete. If you know what completeness is, like it has upper and lower bounds for every ordered set. It's ordered subset, right? And then the complex numbers, right? These are all fields. Now, ones that you might not think of is like Q adjoins square root of 2. Right, so that's a field. So let's think about that one real quick, because these examples are really nice. So it'd be like a plus b square root of 2, or a and b is in Q. Okay, and the addition and multiplication are the usual addition and multiplication, right? So that's the thing, right? So you know that they satisfy all the rules except maybe inverses, right? Because we know that we have 0, we have 1, so that's all fine. Is it true that we have 1 over a plus b squared root of 2, does this have the form c plus d squared root of 2? Like, is it in there? And how do you show that it is? So you're... Yeah, go ahead.
If you multiply it by the conjugate on the bottom and the top, then you have a real number on the bottom, which can be factored out and multiplied. Yep. And then it becomes c plus.
So here, right, we get a minus b root 2 on the top, and on the bottom, we're going to get a squared minus 2b squared, right? Like that. So not only do you get, so there is something interesting here, right? So you actually get this, a over a squared minus 2b squared minus b over a squared minus 2b squared. So there is one interesting point here, square root of 2, right? So like that is my c and that is my d, right? So c plus d square root of 2, right? So we did it. And in fact, these are not only are they real, but they're rational, right? Those are rational. Because the a, b, and c, all of these things are integers, right? In this thing, right? Oh, sorry, no, sorry, they're all rational. So these things are still rational, right? I mean, I've got a rational expression with rationals, right? So it's rational. Why is it the case that we're never dividing by 0? This is a good little subtle point here, right? If I divide by 0, I'm in trouble, right? Why is that never 0? So if it were 0, I'd be able to get that 2 is equal to a squared over b squared. Can that happen? This would give me that square root of 2 is equal to a over b, where these are both rational, right? So it would give me that square root of 2 is rational, right? So it's giving me square root of 2 is rational, but is that true? I think you had this. I think maybe this was a problem you had or not. We talked about somewhere.
Yeah, on the first homework.
Yeah. So square root of 2 is not rational, right? So the fact that this works in part because square root of 2 is not rational, right? It wouldn't work if square root of 2 is rational, right? And you use this kind of construction all the time, right? So how do we actually build C? Well, C is really just R adjoins square root of minus 1. same construction, right? So it's a really common construction where you take a field and you build an extension field, right? So you extend it by adding roots or something like that. So this is all part of what eventually becomes Galois theory, where you try to figure out, can I solve polynomials using roots, or can I do like compass and ruler constructions to create, you know, certain objects and things like that, right? So that's kind of where group theory and stuff got started, back when you look at Galois. And I gave you a nice little video about Galois. The history is interesting there too, right? So if you watch that video. Real quick. Okay, so I know we're sort of running through things. Yeah, so I haven't even said vector spaces yet. So maybe I should just leave it. So a vector space, we have a field. So vector spaces are a little bit different because we have a field sort of sitting there on the outside, and then we've got a structure which is V plus, and then this kind of weird. I don't know how to write it exactly. So it's like C dot. I don't know how to say this exactly with a 0. So, and then this is for every C inside of F, right? So it's sort of a weird structure because it's got two sets. It's got the vectors. So this part's a group. Is a group, a commutative group. So it's kind of funny because vector spaces are actually the most complicated things, right? This part's a field, right? And the way these kind of act with respect to each other, this little operation here is what we'd call scalar multiplication. Right, so the scalar multiplication is really kind of a map, not on one structure, but on both structures simultaneously, right? Going to V. So it's kind of funny because vector spaces are they're the first thing you're exposed to when you take a real class, linear algebra, but they're actually kind of the most complicated of all these structures, right? And then you do all this other algebra, and eventually you get to modules where you have the same kind of structure, but instead of a field, you put a ring in there. I think someone said something about modules in their write-up. Maybe I'll just leave that. I'll leave that to you. I think maybe you have a couple of problems where you're going to show that something's a vector space, right? So you have the axioms, and you get to verify all the axioms for vector space. Let me just really quick. I know we're about out of time, and if someone needs to go, that's fine. But let me just quickly say what needs to be done for showing that Zn is a ring. So Zn with these operations plus n times n. And then there's a 0n and a 1n, all these sort of things there. And the operations are, so what is this Zn? So Zn is going to be the numbers through n minus 1, right? And what they are is the remainders, right? So if I take any m and z, by the way, and I think this is for n greater than or equal to 2. I think we want to sort of restrict like that, right? So any m and z, and I can write m equals q times n plus some remainder. And this remainder has the property that 0 is less than or equal to r is less than n, right? So that's the important thing there. And then this q and this r are unique. Okay. So this is the Euclidean division algorithm, right? And it's actually sort of what you teach kids when they're learning this stuff. And when you do polynomial division, you do it again, right? And in polynomial division, the remainder isn't quite like this. You say that the degree of the polynomial, that's the remainder, is between 0 and the degree of the thing you're dividing by, right? So that sort of stuff. A way of writing, and by the way, there's a whole bunch, like, to prove this thing, you would use induction. So that's a thing we could do. To prove uniqueness, you use a different kind of proof. I mean, there's all sorts of stuff that we could say here. And that's why Crystal and I talked about it for an hour and a half, because we did all that stuff. But just to be a little bit quicker here, this remainder is kind of the important part here. So if I have m equals q times n plus r, then this r is, dang it, the remainder part is what we call m mod n, right? So this is the remainder part when you divide m by n, right? So it's some number between 0 and n minus 1. And here's an important thing. If I want to know that m mod n equals m prime mod n, this happens if and only if n divides m minus m prime. Okay. So we can sort of take this modulus relation and apply it to all of the integers, right? Kind of like we can say something is, I don't know, we can say something is 13 o'clock, right? And we really mean it's 1 o'clock, right? And if you really wanted to do that, if you look at how time's done on computers, right? You look at the current date as a number, and I don't know, it's like 48,000 something or other, right? So, you know, it just keeps circling around and around and around, right? So you can define this on all integers, right? So in some sense you do that, right? So the Zn, another way of doing this is to define 0 bar. Instead of looking at 0, you say it is just all the multiples of n, right? So this would be like, you know, minus 2n, minus n, 0, n, etc., you know, 2n, etc., right? And then like 1 bar is 1 plus all these things, right? So it'd be like dot, 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 minus 2n plus 1, you know, minus n plus 1, 1, n plus 1, you know, etc., right? And so these would be all the numbers in Z that have remainder 1. These would be all the numbers in Z that have remainder 0, right? And you sort of go all the way up to n minus 1 bar, and this would be like, you know, dot, 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 you know, minus 2n plus n minus 1, you know, etc., right? So these would be all the numbers that had remainder n minus 1, right? So you can sort of view it like that. So you can consider the elements of Zn to be these classes, right? And so what happens if you do it that way is if I take two numbers, so take one of these classes and another class. So these are infinite classes of numbers, right? Then the sum of these two things actually turns out to be exactly the same as what I would get if I took the things in each class, added them together, and then put them together in a class, right? So let's say I take 2 bar and add it to 3 bar, right? So one way of doing this would be I have like, you know, dot, 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 minus 2n plus 2, right? Minus n plus 2, 2, n plus 2, 2n plus 2, etc., right? So I have all those guys. So these are all the things with remainder 2. This is 2 bar. And I have 3 bar, which is, you know, dot, 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 minus 2n plus 3, minus n plus 3, 3, n plus 3, etc. All the things that have remainder 3, right? And if I add these two sets together, so 2 bar plus 3 bar, well, this is just the set of all x plus y, where x is in 2 bar and y is in 3 bar. So I'm literally just taking something in here and something in here and adding it together, right? And the result you get will be exactly 5 bar, right? It'll be all the things with remainder 5, right? So that's another way of viewing what this structure is. It could be these equivalence classes, these classes of numbers, right? So either way you think about that. So this is one way of defining the addition, namely that a bar plus b bar is a plus b bar, where we're thinking about these classes, right? Or you could say that a plus b, so now I'm just thinking about these as being numbers between 0 and n minus 1, right? So a plus b, so this is something less than n, this is something less than n remainders, right? So this is going to be a plus b, but now when I take two remainders and add them together, that might be bigger than n, right? So I need to say a plus b mod n, right? So I could define the operation like that, right? And I think that's what's done in the notes. So a plus nb is a plus b. Now this is the plus integer plus, just normal old integer plus, right? Mod n, like that, right? And then what you have to prove or say or something, right, is something like this, that, let's see, what was it we had to do? We had to do, I mean, I'll say the general thing in a minute, but let's see, like, I guess I want to say it like this. So I want to take this relation and kind of turn it back into just something with integers. So I want to say that a mod n plus b mod n. So now I'm just allowing these to be integers, not necessarily between 0 and n minus 1, is equal to a plus b mod n. Right, so this is a thing you can just prove about remainders, right? And if someone wants to stay around long enough, I can prove one of these things about remainders. And then a times b, sorry, let me back out of that. Whoops. Go away thing. A mod n times B mod n is AB mod n. Right? So those are two things you can prove, right? Once you have those things, you can prove by induction that any kind of terms I make out of these satisfies this as well, right? So if I do something like A times B times C plus E times F, right? So I just do this with integers, right? All of this, okay, so I do that mod n, sorry. That'll be the same as A mod n, I'm going to just put all these mod n's everywhere in there, times B mod n, times, C mod, I can just put all these mod n's, you can just put mod n's everywhere, right, in this thing, okay? And so once you do this, the point is when we're trying to prove something like this in the structure Zn, right, you want to show something like, the hardest thing is like distributivity, right? That's like the hardest thing to prove here. So you'd like to show that A times B plus C in Zn, right? So this is, the multiplication in n plus an n, right, is equal to A times an nb plus an n A times an nc, right? So that's the kind of thing you need to prove distributivity in Zn, right? So that's the kind of thing you're asked to prove. That would be one of the distributive laws, right? In Zn, this would be one of them, right? But what you can do from what I just said is you can say, well, what really happens here is this thing is really, so like, what is this really? So it's really this, if you unpack the definitions now, it's just A times B plus C, B plus NC. So now this is going on now in Z, whatever A is, times this. Now this is really in Zn, this is really in Zn. When I multiply them together, they may not be in Zn anymore, right? So this is mod n. By definition, this is how we define that operation, right? And then you can sort of do this again, like, what is this? Well, this is A times, so this is B plus C quantity mod n, right? And so now I want to like pull these mod n's out. I want to say this is really all just A times B plus C mod n. All right, so that's basically what I was claiming above, is I can just sort of pull all these mod n's out, right? So that's what happens here, is if I make an expression using this algebra inside of Zn, right, I can just replace it with the same algebraic expression in Z, right, and then do the mod n at the end, right? And so that's useful because then what happens is I just get this as a general fact, B plus NC, right, is equal to, and now I just write down the usual thing. This is going on in Z, in the integers, mod n, right? And so this is equal to AB plus AC mod n. Why is that? Well, that's because I'm just using distributivity in the integers, right? And then what I can do is I can push this back out to the structure, because this mod n just sort of passes through this, so that this just becomes A times, trying to speed up too much, B plus n, right? A times NC, right? So it's kind of pushes back inwards again, right? So that's basically what you have to do. You have to show that you can sort of go from this to that. Then you go from this to this just in the integers, so that's for free. And then you have to show you go from this back to that, right? And what that really involves is these two things I set up here, right? Those two claims right there, right, is what really is involved in doing that. So I'll add this to, I'll add a video on this because it's an interesting thing all by itself. But for you, but it would be good if you thought about it some ahead of time, right? So this is kind of what's going on, right? And we are already 10 minutes over. So let's go ahead and stop it. I'll make the video for it. In the video, I'm going to do a little bit more. I'm going to do like what I did to Crystal. I'm going to do the proof by induction that you have the Euclidean law and prove the uniqueness of those two things, and prove these two laws here. So this is actually really easy to do. And then kind of derive this more general thing I was talking about down here, and then prove this whole thing. So probably not tonight, maybe tomorrow. I'll add that video. Okay. Any last minute questions? Because it's already like 7:10. Good.
I had a question.
Okay.
What is that like that subscript that's before the letters? What does that mean?
Well, so again, right, we're working in a structure, right? So in general, in a ring, you have a set, and you have a plus of the ring, and you have a times of the ring, and you have a 0 of the ring, and you have a 1 of the ring, right? And so, for example, if the ring is matrices, like n by n matrices over the reals, right? That might be the ring, right? And then the plus of the ring would be usual matrix addition, right? And then the times, so this plus would be the same as, you know, A plus R, right? So that in that case it'd be the plus B, right? And then the multiplication of the ring would be like normal matrix multiplication, right? Right. So you have to say what the operations are. That's the point, right? You have to say what they are. I mean, another option for multiplication in matrices would be to be term by term multiplication, right? You don't have to do matrix multiplication. I could just do it term by term multiplication, in which case the identity would be the matrix with all ones, right? So it'd be a different structure, right? So the same thing's going on here. You've got Zn, which depending on how you want to think of it, is either these classes or the number 0 through n minus 1. And you have to define, what do you mean by addition in Zn? What do you mean by multiplication in Zn, right? What is the 0 of Zn, right? What is the 1 of Zn, right? Now these two are pretty easy. The 0 of Zn is just 0. The 1 of Zn is just 1, right? But for the plus, right? Suppose I'm in Z8, right? And I want to say, what is 6 plus 3, right? But it's not 9, right? It's not 6 plus 3. It's not 9, right? It's 1, right? So the answer is not 9, but 6 plus 3 mod 8, right? So you have to do the mod 8 thing, right? So the point is the plus inside of Z8, right? This plus, I could call it plus 8, right? So A plus 8B, right, is A plus B. Now this is just going on in the integers. Mod 8, right? But this is what your plus is in that structure, right? So that's the point. You kind of see? So it's saying in this structure, this is what the addition is.
Okay.
Right. Kind of see that?
Yeah, I see that.
Okay, cool.
Thank you.
Yep. Cool. Anything else? Quickies? Otherwise, thanks. See you next week. Hopefully I'll get more graded by then. All right. All right. See you guys.
All right. Later, Dr. K.
Yeah. Bye-bye.
Thank you.